So in order to prove the statement, we just have to evaluate the right-hand side on dx and dy. On dx and on dy. So let's do it with the first. That's the wedge product. It's a true form. We plug in two vectors. Now we use the property of the wedge product, which was, the wedge product was defined, we just take the vectors, plug them in the same order. And then we subtract the expression that we get if you plug in these vector fields in the reverse order. So that's the definition of the wedge product. So now we look at these terms that we have here. First of all, we have dx acting on the vector field in the y direction. Well, that was defined to be 0 by the definition of what dx means as the one form. And here we have a term that we also know by definition that if you have dx plugged in this partial x, then what we get is 1. So what we get in summary is that this term is minus d alpha 1 in the y direction. Yes, so that's this expression. And of course, that's nothing else than, now we are like in just like taking the d of a function in the dy direction, and that's of course nothing else than taking alpha 1 and taking the derivative in the y direction. And if you compare this, that's half of the equation. So this term here is exactly this half of the equation. And if you now do it, like do the similar calculation here for the second term, what you end up with, like if you keep track of the minus signs correctly, you end up with the with this term of dx alpha 2. Similar d alpha 2 wedge dy evaluated on dx and dy equals d alpha 2 evaluated on dx. So I would recommend that you do this little calculation at home. So what we get, like in summary, if you add both of these terms, then we get exactly our original right-hand side. So that proves our claim. So let's have a look at an example to make things like a little bit more precise or concrete. So like a very simple example is alpha being the true form, which is just 2x squared dy. So that's a true form. Let's first calculate what d alpha dx dy is based on that formula up there. What I have to do is I have to take the derivative of alpha 1. In this case, is just 0 because there is no part in for dx. So we only have alpha 2, which is in this case this expression over here. So what we do is we take the partial derivative of that guy in x direction to get 4x. So that's just using this this equation over here. Or we can also just use the second equation that we have here, which would be where we have d alpha equals to d, and then we take the d of that function, and we multiply or wedge it with dy. And what you get then is we take d of the function, which would be 4x dy. So that's just like taking d of the function 2x squared. And if you compare now this expression and insert dx and dy, then what you see is that like this term that simplifies to 1. So we get both times the same answer. And this formula also holds more general. So, here we talked about something like in like an open subset in R2. So if we have more general, if D is an open subset of some, say, Rk, then we can write alpha, one form is alpha 1 dx1 plus alpha 2 dx2 plus, and then we get like additional terms here. And if you have an expression like this, what we always get is that d alpha is d alpha 1, and then we wedge it, get dx1 plus d alpha 2 wedge dx2 plus, and then it keeps going on like this. And in this simple case, like it's this formula actually turns out to be way more productive than a similar formula that you end up with like really the components x and y, because you have to keep also track of like certain partial derivatives in x direction and in c directions, and everything gets way more complicated. So in this case, it's way more simple to just calculate, just like use this definition where we take the component as a function, take d of that function, and wedge the direction that you take the derivative on. So it's yeah. And the reason why we talk about this case with like some subset or like for Rk is because usually our surfaces, they live in R3. So if I want to define a differential form on S, it's usually easier to talk about the differential form on R3 and then just restrict it to S and say like, okay, like this differential form on R3, I can plug in arbitrary tangent vectors, and what I'm doing now is like I only put in like the points of S, and I only put in tangent vectors that are tangent to S. So I can restrict every differential form that lives on R3, I can restrict it to get a differential form on S. So that's why we talk, sometimes also we have to talk about differential forms on R3 instead of just something that is two-dimensional. And there's a property that we have here that you essentially just take, if you have a function in front of dx and dy, and we just take d of that function and wedge it, that generalizes to, and we have the following properties of the exterior derivative. So if f is a smooth function, on S, and alpha a one form on S, then also the product of the function and the one form is a one form again. So if I just plug in a vector, I plug in alpha and then just get a number, and then I multiply it by the evolution of the function at that point. So that one is a one form. So we can take d of that one form to get a two form. And if you look at this, what happens upstairs, what an actual guess would be, what we do is we take ef to get a one form, and then we wedge it with alpha. But there's one part that is missing. Here we also take the variation of alpha in this formula, right? Like if we take also the variation of alpha that we want to calculate. But on this formula, as of now, we only take the variation of f and just some values of alpha. So we also have to take the derivative of alpha, and what we do is in this form, where we take the variation of the alpha and then just multiply with f. So it's kind of some form of the product rule or some Leibniz property. So if you would consider the alpha to be just a function, would you get something of the form, if you have a product of two functions and you take the derivative, is something that you take the derivative of f, like the first actor, times the second, plus the first function times d of the second function. So it's very similar. The only difference with the normal product rules is that we now have here the wedge product, so that we really can make sense of a functional or like df, like, because we have two one forms. So it's the Leibniz property. So that's the first statement. And the second statement is that if we have a function, we can take the d of that to get a one, and then we take d of that one form again, we get a two form. And then it turns out that this one is always 0. And yeah, I don't want to prove both of these elements. The first one, we can really just use the definition of, that was like on the blackboard over there, just really calculate what happens on the left-hand side, plug in two vector fields in a chart, calculate all of these terms, and then reduce it to the ordinary Leibniz rule, and then compare these ones with like evaluation of this side. This one will actually be your homework, at least in the more simple case where f is just like a function of some open subset. Okay. Yeah, so that's all I wanted to talk about for taking derivatives. So I think it's a good moment to go in a break. And then in the second part we talk about integration. Huh? So let's continue in 50 minutes, 20 past, and then yeah, talk about integration.
this part I didn't understand why this definition is not good. Like, what's the problem for this definition?
So the problem is that in order to, you have to make sense of this term, like what alpha, what it means to plug in v2 into alpha.
Yep.
V2 is just a tangent vector,
Yep.
while alpha is like a one form. So one form is like defined, it wants to eat like a tangent vector at every point, but it wants to eat the tangent vector at that given point. But we only have like one tangent vector. So that vector is, for example, this vector, it's pointing outwards. And we want to say, like, what is the value of alpha at that point? Like, what is, like, how do you do that? Like, this one is only defined here, and we only know there's one vector. But alpha is, like, maybe also defined here, and we want to take the derivative. So we want to compare the value of alpha here with the value of alpha here. But this one vector is only defined here. So we would need to extend this one vector also to here, and then like plug that one in alpha, and then we have something that we compare. So that's the problem. that's per definition. So like there is also something that like eats two vectors, but is symmetric. That will be encountered later in the course. But like the differential form is by definition antisymmetric. And it has something to do with the integration, which we will talk about now.
In physics, the exterior derivative is always have this factor. Yeah, but here we do not divide in two. I'm wondering why.
Yeah, so yeah, it's like the question is what you define as coefficient in front of the like what is this alpha? So it's like so in one form it's easy, right? It's just but like a two form would be some function or some function so dx. But that would be a and now the question is, do you for this one beta 1 2 or do you call it beta 1 2? Yeah. So and that's actually just like it's not like beta is the correct position here would be a beta 1 half. Like it's the coefficient is not like here it's really the coefficient in front of the x is like alpha 1. And here it's the coefficient but it's like the half of the 1 over 2 in front of. So this is just one interpolation. Yeah, so it's really like the coefficient are called like this. So that the one here not on the coefficient as that. That's why you generally you have higher orders but you get so that's by definition. The coefficients are not like that's why we get x. This is just the difference in yeah, so it means like essentially what it does because what you have is like six lines. What you have is E1 dx y plus and then we have a function plus another function e1 dx. And then we just like absorb that we get a minus. So like, that's why we get like 2 times the same thing and then you get in factorial it's like the same kind of expressions and then you
Last thing.
Yes.
How does this work from this to this?
So that's the definition of the wedge product, which is like if you have the wedge product of two one forms and you plug in two vectors, is what you do is like you take each of these vectors, plug them in the one forms, and then multiply the result, and then do it the other way around. So that's really just the definition of the wedge product.
Okay. Then how does this thing like? So is this one equals to 1, or how do you say, like, because this is 4x and this is 4x dx?
Yeah, so this one is really already evaluated on two vectors, so that's just like a number or a function. While this one is really just having still like
so when you plug in those two into this,
yes, you get like the same 4x again. Okay, let's continue. So we would like to talk now about the counterpart of differentiation. But maybe before, one remark about essentially this property is that we get two classes of differential forms. And it's just some definition. And so that the first thing is like alpha, which would be a one form called closed if d alpha equals 0. So that's closed means that it's d alpha of it vanishes, and it is called exact if there exists f. So it's globally defined. So globally defined function on the surface such that df equals alpha. And then this property here implies that if you have a function such that d alpha equals df equals alpha, then this property automatically implies that it's also closed. That we then d alpha equals to 0. So that means that every exact form is also closed. But not every closed form is exact. So if you're a physicist, then you can think of a one form essentially as a force, and then closeness means that it's like conservative, that it doesn't depend on the chosen path that you take to calculate the work. And exact means that you have a potential. And then the statement here that we proved is saying that like every potential gives you a conservative force, but there might be some conservative vector fields which are not coming from a potential. But that's just like some names for now. So not, these are called just closed and exact. Good. So now we can talk about integration of a two form. So the inspiration comes, of course, from the integration of the one form. So first have a look at that case again. So if alpha is a one form, then and see a curve. So the curve from A to B into S. Curve, then we were able to define the line integral along that line or along the curve of alpha. And the way we did that was we were reducing it to a normal integral over the time. And what we did was alpha evaluated at a certain time instance. And then we take the derivative of t. So that was for one form. So now we have to think about what it would mean to calculate the integral over a two form. So for a two form on S. So in a two form, we can't just lose like a curve again. If you have a curve, then we have a tangent vector, and then we say we plug in the tangent vector twice in the two form to get a number, but that number will always be 0 because two form is antisymmetric. So if I plug in twice the same vector, I just get 0. So we can't just like take a curve. That like doesn't give you like you can't integrate a two form along a curve because that will always be 0. So we need like something that has like two directions. So we need to integrate along some two-dimensional object. And the idea will be just really take like a sheet of paper and then integrate essentially along the sheet of paper. So we have kind of like a sheet of paper. We plug that in our surface. So that's our surface. We plug that around the surface, and then get here we can like certain like on that kind of like curved surface we have our two form, So we can evaluate it in two directions, and then we get a function and we can integrate that function. So that's the idea, essentially to reduce it to a two-dimensional objects. So what we need is like a two-dimensional version of a curve, and for that a rectangular or a rectangle region in S rectangular region in S is a smooth map. I usually write it as a capital R from some rectangular region into S. So really you should think of that as really like having a sheet of paper and then plastering that on some part of your surface. So that's a rectangular surface. And then we first define the integral over that. And then later we will talk about how can we make like sense of the whole integral over a surface by just like pasting rectangular elements over the surface and then summing up the contributions of each one of them. So we would once have like such a rectangular region. Then we can define integral of the two form beta over rectangular region R is given by a very similar formula on the left hand side. So we take inspiration by this formula upstairs. So what we do is we have a certain curve where we change R in one direction. So we can make sense of this as a tangent vector at the point xy of S given by the curve we have there. So that's a curve in S, and then it represents a tangent vector at that point for t equals 0 at x of y. So it's a tangent vector that's very similar to the definition of dx along phi, where phi was a chart, but now we have like slightly more general things about the rectangulars. So that's it's a certain tangent vector that is like corresponding up there to a c dot. So it's like the tangent vector. And the idea is now that we have our two form, we plug in, so a c of t we replace with rx of y, and then we have to specify two tangent vectors, and what we do is we plug in dx and dy, the partial derivatives. this is a tangent vector, and similarly, dr to dy is a tangent vector. So this one makes sense. We can plug this into a beta. We get in total, what is this? Is a function of x and y, and then we just take the integral over ab and c of d of the function. Here we have first take the dy and then dx. So that's a definition. Just take like the change of r, which gives you tangent vectors, plug them in the beta, and then integrate the result. So by for linear, just like as a side remark, for linear, it doesn't matter if you're the rule of integration, if you just integrate first over AB and then over CD, or the other way around, the order of the equation. Okay. So let's have a look at an example. So we can, for example, consider the rectangular of 0, 1 in R2. And we really consider this as like the standard rectangular, which we can parameterize just by S and T. So it's really a 0, 1 here, and then 2 here. So that's the rectangular version R. And then let's say we want to calculate the integral over x dx wedge dy. So that's a 2 form on R2, and we would like to calculate that integral. So let's see what we have to do. We have to calculate these two vectors, dr times dx and dy. So let's do that. Of course, dr in S, or maybe I should use x and y here. So dr in x direction is of course nothing else than 0, 1. So I take the derivative here in x direction, just get a 1 here and 0 there. And we can write this one as in a more standard way as the vector field that goes in x direction, so dx. And similarly, dr dy equals 0, 1, which would be the y direction. So by definition, this integral would be the integral over 0, 1 and the integral over 0, 2. And now we have to go evaluate this 2 form here at these two vectors. So that will be dx and dy by definition. And so we can see if we plug in dx, dy in the wedge product, what happens is that dx hits and gives us 1, dy and d1 hits, which gives us another 1. Dx. And then if you pair them around, then you get like 0. So what you see is that this one essentially comes down to x times and then dy dx. So that you can calculate, and I think it should be 1. But yeah. So you just integrate now this expression over y, that's a constant, it gives you 2. And then you integrate x over dx, which gives you x squared over 1/2, and then you insert the boundaries. So note that, for example, that like if you change the order, then we get -1. So it really depends on the order. So this integral here, the ordinary integral, where we have just like dy and dx, doesn't depend on the order. That's just essentially Fubini. If you have the right conditions, then it doesn't matter in which order you integrate. But here, it's really depending on the order of like the dx and dy with the wedge product, because they manage, they give you a contribution of -1 if you change them. So really be careful to really write it like as dx wedge dy and not just x dx dy. So that's like really important. Okay, so that's the definition of the integral, but it's maybe not the most insightful in telling you what it actually computes, right? Like you have a 2 form, and you calculate that integral, it gives you a number, but you would like to understand what is the number in order to get some feeling of what you calculate actually. So let's have a look at like some particular cases to get some ideas of what this surface integral actually calculates. What is this number? What is the meaning? So let's assume that alpha, say beta, beta is of the form for f1 dy dc plus f2 dc dx plus f3 dx dy. And that's the 2 form on, say, let's say on some, maybe some open subset, but let's say that it's defined on the whole of R3, or some open subset of it. With small functions which we the small functions f1. And we can also think of f, where we plug all of them together, so f1, f2, f3, as a function that eats a point and spits out a vector, and we can think of that function as a vector field. As a vector field on R3, or precisely on an open subset of R3. So we have just like some part of our space, and then at every point we have like a vector, and that vector field might change. So we have like some changing vector field in R3. We might restrict that vector field to some surface in R3, but for the moment that's not so important. But what we can do is that R dB and CD U be a rectangular region. And then that's denoted by Tx, xy. Be just dr, dx, and xy, and ty, xy. The two vector fields. So essentially what you have is like that rectangle, and you might like consider that in space like that. And then we have like at each point of the rectangular we have like something in x direction and something in y direction. And what we do now is we want to talk about the normal direction. So what we do is we take the the product of the two vectors